Welcome, one and all, to the Cool Worlds podcast with me, your host, David Kipping. This week, I have a special guest, and that is Natalie Batalha. She is a professor of astronomy at UC Santa Cruz. She was also named in 2017 a Time 100 person. So that's really the top 100 influential people in the world. Pretty amazing for a scientist to make that list. And the reason why is because of Kepler, which she was one of the lead scientists. So Kepler, not Johannes Kepler, a person who lived a long time ago. Rather, we are talking about the Kepler mission, a NASA mission that launched in March 2009. I actually have right here, for those watching on the video, a badge of the VIP guest pass to watch the launch. I was not there. This was actually when I was only a year and a half into my PhD. So I was still in the UK, dreaming of trying to get over to the US and getting involved with this mission because, of course, I knew about it. It was big news that it was coming up. But this pass was given to me by Dimitar Sasalo, who was a mentor of mine at Harvard. He was there, and I really treasure this little gift he gave me of what, imagining what it would have been like and having the real pass of the VIP guest pass of the Kepler launch. So it was a shame I couldn't be there because that mission truly was a transformative episode in the history of astronomy and even science, I would say. For in that mission, we discovered thousands of exoplanets. And if you look at the current catalogue, even today, even though the Kepler mission ended many years ago now, if you still look at the current catalogue, which has almost 6,000 exoplanets listed, I think something like 3,500, 4,000, so the majority of those exoplanets were actually found by Kepler. So it's an incredibly successful mission. It was a mission designed really to try and get as small as planets as possible, even as small as Earth-sized planets, transiting in front of their stars and seeing those little dips in light. And Natalie was really instrumental in leading this mission, both strategically and scientifically. And it was a real pleasure to have her on the podcast today and get to ask her all about the history of this incredible mission, but also the future. So we're going to talk a little about James Webb, what's coming up there, because Natalie's also been a leader with James Webb Science. And even further ahead, we're going to talk about imaging, what might be possible for the next generation of missions. So please stay tuned, and I hope you enjoy this episode. So Natalie, it's really an honor to have you here. I said this to you last night at dinner, but you're one of the people in the field of exoplanets I've really looked up to my entire career. So very grateful for you to be here today.
And vice versa.
Oh, well, that's very kind. I sort of cut my teeth on Kepler and as a grad student, and that mission for me was one of the most historic and important phases, both in the field of exoplanets, but also in my life. And of course, you were one of the architects and leaders of that mission. So I thought we should just start by maybe talking about the history, a little bit of that mission, if you don't mind. And maybe you can tell us the story of how you first met the principal investigator, Bill Barucki, and what those early days were like.
Of course, the history of Kepler goes back way before me. Mm-hmm. I think it dates back to a paper in the 1980s, perhaps, that Bill Barucki wrote with a co-author. I think his last name was Summers, but it was a paper about photometry. Just with modern technology and CCDs, we could not only get better precision on the photometry, but we could observe many stars at once. And so I think he recognized that provided a fertile ground for transit detection, for the transit method, which required that you looked at a lot of stars. So that was in the 80s, and Kepler was proposed. Well, the idea of Kepler was proposed many times and was rejected, and all for reasonable, motivations. Could we really get 10 ppm, 20 ppm part per million precision with these CCDs? That hadn't been demonstrated, so we had to go back to the lab, and in collaboration with people at UC Santa Cruz, actually Lloyd Robinson, they showed that you could indeed get that precision in the lab.
And I'm guessing this is all happening prior to 51 Pegasi b, the first confirmed exoplanet.
Some of it is concurrently. I think the work with Lloyd Robinson might have been around 1996.
And 1995 is the first planet.
1995 was 51 Peg b, yeah. And then do you have the computational resources? You know, do you have the technology that you need to analyze the photometry of so many stars with so much data?
Yeah.
Right? Now it seems obvious to us. We could do it on our laptops.
200,000 stars? That's easy. Yeah, no problem.
No problem, right? So, but back then it wasn't so trivial. So
Yeah.
we had to demonstrate that. And I think the final thing that was really, well, there were several, but then one of the major weaknesses or concerns was that you wouldn't be able to tease out the signal of a transit, this dimming of light, from the modulations in the stellar brightness just due to star spots rotating in and out of view.
Which is what you were working on during your thesis?
Yes. So during my graduate studies, I was doing Doppler tomography. So mapping star spot distributions on stars like the sun, but younger, kind of baby and teenage suns. And, so spots were very much on my mind. And not just spot distributions, but also things like the evolution of spin down, how stars lose angular momentum, right? Because rotation is connected to magnetic activity, which is connected to spots. So all of those things are related, and I had been thinking long and hard about all of those issues. And so when I was still a graduate student, I was about to defend my thesis. I remember visiting one of my collaborators, Gabor Basri, at Berkeley, and he had on his desk this report on something called FreeSIP. He had been involved with kind of like a red team review of this idea, and FreeSIP was the first acronym for what became Kepler. And I was waiting for him. He wasn't in the office yet. I was early, and so I kind of leafed through this thing and then asked him about it later and learned what this guy, Bill Barucki, was up to at NASA Ames. That was my first awareness. So that would have been like mid-1997, maybe towards the end of 97.
So by this point, it had already been proposed like 4 times or something and rejected?
It was proposed first in 92, and then 94, and then 96. So it had been proposed 3 times. They must have, at that time, been getting ready to put in the 4th proposal, which also was rejected.
Yeah.
It was in that proposal, my understanding is that it was in that proposal that Ed Weiler, who was somehow involved with the Discovery program, he was also an expert in stellar activity, and he expressed this concern about the stars and their intrinsic variability.
So whether you could distinguish a dip from a planet versus a dip from a star spot rotating into view.
Exactly.
Okay.
Yeah, could you distinguish those things?
So how did you convince them you could?
Okay, so I see this report. I defend my thesis. I go to my first postdoc in Brazil. My husband and I had to move back to Brazil, and I'm there. And I kind of cold turkey, is that the right metaphor? Cold turkey, reached out to Bill Barucki, wrote him an email and said that I'd heard about this method and that I was skeptical. And I explained why.
That's bold of a freshly minted grad student to do that.
Yeah, what hubris, right? And he immediately responded and invited me to go visit and said that this was one of the reasons why the latest proposal had been rejected, and could I come and work on him with that and on that question and try to make some headway. So I did. I went to NASA Ames. Now this is like 2000.
So he offered you a job in that email? He said, I'll hire you if you
He
come
asked me
here,
to put in a proposal for the NPP fellowship program.
Okay.
So I wrote a proposal, and I described how I would approach this problem. And it was awarded. I got the fellowship and started at Ames like around January of 2000 after my first postdoc.
All from that cold email?
Yes.
Yeah.
Yeah. So, it was a confluence of things that made the case. On the one hand, you needed to understand how many of our stars would be truly too variable to make this happen. But on the other side, there was this signal detection part, and there was a young, talented electrical engineer, PhD in electrical engineering, who was an expert with digital signal processing and time series analysis.
I can guess who this can be. Yeah.
This is John Jenkins. Yeah. Amazing human, extremely brilliant. And he used SOHO data of the sun to understand this problem. And he's the one who showed that through these computational techniques, you could actually isolate the different signals because they would usually occur on different timescales, right?
Mm-hmm.
So the variability of a transit might be smaller than the modulation from spots rotating in and out of view, but the timescale should be separate, and also the duration of the transit should be quite short compared to the normal variability that you see from spots. Now, that's not going to be the case if you take a sun rotating at 29 days or something, its spin period, and you make it spin faster. Now you start to get modulations that do look like transits. And so where is that cutoff? And so you define that, and then you go to the galaxy, these synthetic population models, population synthesis, and you say, all right, how many stars in the galaxy do you expect to be that young and that active? And you can do those calculations. There were papers in the literature that described how stars lose angular momentum, at least G-type stars, G's in case. It took much more to disentangle that behavior for the M stars. But we could make some headway, and that's what we did.
Was there ever a temptation to use multicolor photometry with an early... Because I know, obviously, Corot had this 3-band photometry, which ended up not working out too well. This is a European, almost kind of precursor mission to Kepler. And I suppose a limitation in this sense with Kepler is it sees everything in just one color.
Yeah.
And that color information could help you distinguish between spots because they would be highly chromatic, you would expect. So was there ever a temptation in that 4th or 5th version of the proposal to revisit that question?
I mean, that was the narrative early on. If you read the 1992 TOPS report on the future of detecting other worlds, and in the 1 or 2 pages that they devote to transits, they actually point that out as a potential problem. And in order to distinguish this from other astrophysical phenomenon, you're going to have to observe in multiple colors. The problem with that is now you've got narrow bands. You're isolating such a narrow region of the electromagnetic spectrum that you lose photons, right? Kepler, first of all, was very simple in its design, which helps. But also it was broadband, so you're just getting a flood of photons so that you can really increase your precision. And so it's a sacrifice. You have to choose one over the others. Like if you want to do colors, you're going to have a filter wheel potentially, or some other kind of engineering that's going to increase your risk.
Right, Corot had the very complicated PSF, I think, right? It kind of had like a little mini prism and it split the light up, and that was very difficult to model in the end.
And it just puts more elements into the optical path. Every time you do that, you introduce risk.
Yeah.
Something's not going to work, or so you're going to have a failure mode, or, I think Kepler was really successful because of the simplicity of its design.
So you were obviously involved in the mission from the very earliest, not the very earliest, but so you did correct me on that, but pretty early on.
I mean, it was like 20 years of my career. Yeah, right.
And obviously you rose through the ranks and became a project scientist and mission scientist during your career with Kepler. But maybe nothing did, but did you feel like anything changed in terms of the operation of the mission or the culture within the team? How did the mission look from the beginning to the end? What sort of evolved?
A lot of things evolved. I mean, Bill Barucki is this just singular, unique character. Has all the personality traits of a pioneer who could trailblaze this path forward. He has this quirk where he never takes criticism personally. Just doesn't internalize it.
Yeah, must have done for that email not to have offended him, right? Yeah.
Yeah, well, I don't think I wrote it in an offensive way.
Yeah.
I was super interested. I was curious, and I think I expressed that. Wish I had that email, actually. I'd like to go back and reread it. But he has that kind of very unusual personality trait of persistence in the face of criticism, and not listening or not internalizing criticism as something personal and using it as an opportunity to improve.
Wow, that's a superpower right there. Yeah.
Right? It's a superpower. Seriously.
Yeah.
I often think in my head, okay, it's time to channel my inner Bill Barucki. So he's like a CEO in that way, he's just very trailblazing and just kind of bowls his way through, not bullies, but like a bull, just kind of getting it done. And
very focused, yeah.
Just getting rid of hurdles along the way. but but then once the mission was funded, I think he didn't enjoy, leading the science. It's like the more kind of managerial things. And we had this saying during the mission that exoplanets were hard, but people are harder. So there was a cultural change in terms of how the mission would be led. We started instituting working groups just because there was a lot of work to get done, but I think that changed kind of the inclusion factor. At first, there was the idea that only funded participating scientists and co-investigators would be in these working groups, but that, we soon realized that we needed all hands on deck. You say that you cut your teeth on Kepler. I think the exoplanet community very broadly cut their teeth on Kepler. It was the first big transit mission, right?
Many careers were started from that data set.
Oh my gosh, so many.
Probably the biggest legacy of the mission, if anything, right? It's not the thousands of exoplanets, but the fact that we have so many people who were trained from working in the trenches of seeing the first data really come down from Kepler.
Yeah. It really does exemplify the difference between like the Doppler community, who work more independently in these small groups, these like niches of expertise, versus having a big NASA-funded mission where, what you're trying to do is so broad and so ambitious. You really need lots of different expertise to weigh in. You need a lot of people to think about different aspects. And I recognize that keenly because we were trying to run a ground-based transit program before Kepler up at Lick Observatory. And so the whole problem with astrophysical false positives was really top of mind for me. And back then, we didn't have all these techniques for distinguishing between, a background eclipsing binary and an actual transiting planet. Those things we were kind of inventing on the fly as this was unfolding. So, binary stars. I wanted a working group who cataloged binary stars. I wanted a working group who was thinking about stellar activity. And then we discovered transit timing variations. We need a working group to do that. Architectures. I mean, there were myriad things. Yeah. Understanding the false positives, the astrophysical false positives. A lot of them are interesting in their own right. We found...
So would you say the science interest therefore kind of ballooned? That maybe initially ballooned, was a singular focus on Earths and it kind of expanded?
It grew in scope.
Yeah.
I think I and others, we mostly... I, Bill Barucki, and Dave Koch was the deputy PI, but he was diagnosed with ALS like right after launch, which was just devastating. And he retired early, and so I was kind of thrust into that position. It was abrupt and surprising, and you just kind of have to put on your big girl pants and do it,
Yeah. You did a great job of it, yeah. So.
Thank you. So, I was reaching out to people in the community asking if they could lead various efforts to try and increase that scope and broaden what we could accomplish. Yeah. So that was a cultural change. Operating in big teams and mobilizing the community, I think. I'm sure that has happened before Kepler. I'd never been part of that, so this was a first time for me. I can't actually point to other examples, but I'm sure like the Mars rovers and things like that must have felt the same. I don't know if they had the same kind of community participation. But anyway, I mean, it was that kind of culture shift that I think really made an impression on me. I think I saw firsthand like the power of it, and I wanted to kind of play forward those lessons in other research endeavors that happened afterwards.
We'll be right back after this short message. This episode is sponsored by Incogni, a fantastic service that I've been using for a couple of years now that I think solves a common frustration that we all have in everyday life. Because here's the deal, it seems like every day we are forced to enter our names, addresses, telephone numbers, and other personal information into some kind of online form. Companies harvest your data. We all know that. But what makes it even worse is that they then sell that data onto data brokers without your permission, and they in turn then trade it to somebody else. This not only leads to spam mail and calls, but can even include the leak of private information like your employment history and social security number. Now, you don't have to put up with it though. You could, in principle, write to these data brokers and request your information be deleted, but they'll probably just ignore your message unless you pester them over and over again. And this is where Incogni comes in, because they are a service that take the fight off your hands. They scan databases for your information and then demand that your data be deleted persistently. For me, personally, they have successfully removed my information from a whopping 786 databases to date, with another 60 in progress. And if I were to do that myself, it would have taken me almost 600 hours of my time. If you care about your data, then you need Incogni. So to get started, head to incogni.com/coolworldspodcast and use the code coolworldspodcast to get an exclusive deal of 60% off their annual plan. Once again, that's incogni.com/coolworldspodcast, code coolworldspodcast. Now back to the episode. So the primary mission was just over 4 years. And we say primary mission because that delineates from what became K2, which is really instigated by this failure of a second reaction wheel. So Kepler had...
On my birthday.
Oh, was it? Oh, no.
We
How
heard about it
unfortunate.
on my birthday.
Yeah.
Our communications director, Michelle Johnson, and I were
What a
having
birthday
a
present that
birthday,
is.
celebratory birthday taco, and we got the message on our phones.
Not a great
It was
birthday.
such a bummer.
So it is, I've always sort of wondered about what happened behind the scenes with this a little bit. So now I have you, I can kind of ask you about this. And that was, there were 4 reaction wheels and 2 of them failed in the first, just over 4 years for 2 of them to fail. And this, of course, there's other missions which have reaction wheel failures, but we have mission like TESS flying right now, which has now flown for like 6 years. And I don't think it's had a single reaction wheel failure. So was Kepler somehow extremely unlucky that those 2 failed, or were there suspicions or hints that that was a risk early on? There was something maybe...
They certainly knew that it was a risk early on. There were indications of problems before launch even. And I don't fully remember the history. I wasn't in a leadership position at that time before launch. But I do recall there being, an alarm was sounded, but there just wasn't enough funding in the budget to make it happen or to do really much about it. I'm sure that they did some due diligence to try and mitigate potential failures. Sadly, that didn't work out for us, as you said. Now, I learned recently, talking to a colleague, that other missions were using the same reaction wheels. I think it was GALEX that was using the same reaction wheels, and they learned about these failures and like, oh no, what do we do? And I said, well, did you switch to different reaction wheels? I think that wasn't really an option. And the problem was that it was kind of stochastic. Like the failure mode is just probabilistic. Like you don't know.
It's like an atom decaying or something. Yeah.
You don't know when. I mean, things just get kind of stuck inside. It's not exactly ball bearings, but something like that. The particles break apart, and you have this failure mode that you can't predict. So I remember after the first reaction wheel failed, we were looking quite closely at the behavior of the other reaction wheels, and we could already discern like which ones might have problem in the future. So I think that's what GALEX did, and they just tried to pick and choose the best ones. And now I remember that before launch, what was being asked for was additional redundancy, and that's what
like a fifth wheel.
We didn't have any budget to make that happen in the time.
Because I heard originally the antenna was supposed to be larger as well. So instead of having this 30-minute cadence, it was going to be a faster cadence. Yeah.
We were supposed to have an articulating antenna that could communicate with the DSN stations, and that got de-scoped to save money to a fixed pointing on the body,
which gives you the quarter gaps. Is that the origin of the quarter gaps?
And that gives you very specific windows for data downlinks.
Yeah, so Kepler has to actually point away from its field to do the downlink back to the Earth, and then it can go back.
Yeah, you had these downlink windows, but there's also, don't confound that with the roll angle, right? Like every quarter we had to roll just because you're going around the sun, but you have to stay pointed at the same star field, right? Yeah. So when you come over here behind the sun, you don't want that that angle to be too close. You want to
Yes.
avoid sunlight from getting into your electronics, so you have to keep that angle relatively high. So you're going like this, and so every once in a while you have to roll to maintain that orientation.
I mean, it turned out the 30-minute cadence was fine. It was not really a major limitation to have the 30-minute cadence. I don't think that was a big sacrifice in the end, but obviously the reaction wheel was something that it was more substantial to lose. But K2 was this very successful second version, Kepler Reborn, and it really was quite ingenious. Were you involved in the inception of that solution?
No, not really. No, that came from the engineers.
Okay.
I don't even think that was at Ames.
Can you just describe it to us, the solution for those who don't know?
Yeah, so you have these 3 reaction wheels that serve kind of like as gyroscopes to maintain the pointing stability. So each of these 3 axes is like controlling a certain angle or certain axis of rotation, right? And now you've got 2, so you're open loop on the 3rd axis, and you're going to have pointing instabilities. What do you do? So the engineers came up with an amazingly clever solution, which should go down in history. They decided to point the boat upstream effectively, right? So imagine you're in a canoe, and the current is kind of tossing you all over the place. And then you take your boat and you rotate it directly into the current.
And the current here is light from the sun.
The current is the radiation pressure from the light streaming at us from the sun. Yeah, analogous to water flowing in a river. So they leveraged the symmetry of the spacecraft, the fact that the spacecraft had an axis of symmetry. And so they pointed that spacecraft right upstream so that the pressure from in our analogy, the water, or in actuality, the radiation pressure, pushed evenly and kept the spacecraft from rolling side to side. And so that controlled the 3rd axis. Now, the downside is that you have to point along the ecliptic. So that's going to limit which fields of view you can observe. You can't observe the Kepler field, for example.
Yeah. The original Kepler field was
the
lost.
original Kepler field, which was like at 79 degrees
too far north
latitude. So it was too far north. But on the other hand, so I was sad about that. I was really sad about that because one of the main reasons Kepler was funded was to compute the frequency of potentially, or planets orbiting in the habitable zone that are potentially rocky or terrestrial-like. So, we'd had just about exactly 4 years of data, but because the stars were a little more variable than we expected, we needed more data to be able to pull out detections at those orbital periods and sizes. We were so close.
So if you got to like 6 or 7 years of data, you probably would have...
No, for the prime mission, we got exactly 4.
No, but if you had, I'm saying, if there was a what if where you got to that point, you probably would have hit.
We were already preparing an extended mission proposal. In fact, I don't remember the details, but it could be that...
Wasn't it already in effect? So
I was going to say, I think it had already been submitted.
3.5 years was the primary mission.
The primary mission was done. That finished in 2013. That's when the second reaction wheel failed. We would have already submitted our extended mission proposal, but then the second reaction wheel failed and a halt was put on it, and we had to go back to the drawing board and resubmit a new proposal. And that process took like almost a year. I mean, it was a lengthy process involving engineers, but then also reconceptualizing what the science drivers would be.
So Kepler was just doing nothing in that time. Yeah, it was just adrift.
Oh God, we had so much to do. We were so...
No, but the actual telescope itself
the
was
telescope
just,
itself was
just,
not, that's right.
Yeah.
Was dormant.
Yeah. So yeah, you mentioned Earth, and obviously Earth is the occurrence rate of Earth-like planets, of which there's contention about how to define, but roughly an Earth-sized thing, plus or minus whatever, 20%, 50% within the canonical habitable zone of a star. And I did a video about this on the Cool channel a while back. I called it 50 Lost Dreams, because in the original Kepler planning documents, proposal documents, there was an expectation to find 50 Earth-like planets in some of the very first sort of Bill Barucki.
In the very first, after the downscopes, I think that got reduced, but it was like tens. Yeah, that sounds about right.
And obviously we ended up with essentially 0 of, around, I mean, there's planets in the habitable zone which are Earth-size around M stars and K stars that Kepler found, like Kepler 186f I can think of. That I think was Elisa Quintana, I think. led that paper.
186F is orbiting an M dwarf.
Yeah, so there's like some planets like that, but around a true sun, I don't think we quite
I still
got
think
there.
Kepler 452b is going to be a valid candidate. The problem is we had candidates there, but you couldn't distinguish them reliably from what we call rolling band artifacts that are commensurate with the orbital period of the spacecraft. So it introduces a systematic that can mimic transit. It's like a moire pattern that drifts across the detectors, and what's drifting is like a voltage signature. And so it's causing these apparent flux changes, and they can look a lot like transits. We did a lot of work to try and understand their frequency. It turns out that the systematic, it's not always a dip. Sometimes it's a peak, so it goes in both directions. So if you take all of the data and you flip it over, any physical transit is going to become a positive outlier. So then you look at the frequency of these transit-like things that are going the other direction, and that gives us some handle on how frequently they occur. And that was the problem. Like, we had all these candidates, but this large fraction of them are expected to be these rolling band artifacts, and it was impossible to distinguish. So we have some candidates, but we just don't have an instrument to go back and confirm their viability.
Yeah, I know we put in a proposal to observe Kepler 62F, which is one of these almost Earths, and I think Chris Burke had followed that up with Hubble to do exactly this, to try and like confirm for sure. I don't think that work actually ever got published for some reason, but the data's been taken, so maybe someone will do that soon. But I guess the real point is not the individual cases, but the overall population. And so I was surprised when I did this video looking at the literature of how diverse the estimates are. So I'll just give you two numbers. Steve Bryson in 2019 got 1.3%. Plus or minus about 1% for the frequency of Earths in the habitable zone. And then you've got John Zink in the same year, both using the same data set, DR25, the latest Kepler data set, and they got 22% plus or minus 1%. I think that 22% kind of became the canonical number that the Louvois team, which was an imaging proposal, and then now the sort of rebranded as the Habitable Worlds Observatory, essentially. That's sort of become a canonical number those teams have locked in on.
Well, there's a more recent paper, I think, by the Steve Bryson group, which I'm a part of, to weigh in on Eta Earth. I think the 2019 paper was, maybe it was the 2019 paper. Was it that long ago? There were like 3 papers that Steve published that looked into this question and improved upon things. And I think converting the Kepler database into an actual occurrence requires a lot of different bias corrections, both in terms of completeness, what we call completeness and reliability. So completeness. Of all the ones that existed, how many did you actually detect, or could you detect? Were you capable of detecting? It's going to be a fraction. It's not 100%. And you need to measure that. But the other one, which is more complicated, is reliability. Of the ones you detected, like we were just talking about with the rolling band artifacts, how many of them are expected to be bona fide candidates? And we could divide that in 2 categories. One is a reliability with regards to astrophysical mimics, other things in nature that mimic a planet transit. The second one are these instrumental artifacts. And so I contend that the Bryson paper is actually the only paper that did Eta Earth that considers all of those factors with all of the different data products that were delivered at the end of mission, which was around 2017, 2018. And even that required extrapolation, because as you said, we could get that occurrence out to periods just short of 365 days and maybe just a little bit larger than Earth. And so you have to assume that it's going to be uniform beyond that and extrapolate what that number is going to be.
So I guess my point is there is a diversity of solutions here, and I guess you have to sort of pick favorites a little bit when you're thinking about these next generation missions, because that number is quite crucial for how large do you build the mirror.
There was an Eta Earth estimate that was published like less than a year after launch. They're not all created equal, right? They're not it'd be great to have like a data challenge where you sit down and everybody tries to do that. But you have to start with the same input parameters, the same final catalog, uniform vetting, completeness and reliability metrics. Now we have the Gaia properties as well. So you have Kepler plus Gaia, which is just increases the superpowers of this mission. So I wouldn't characterize it as picking favorites. I would just say that the state of our knowledge grew. It just grew, and it's still imperfect.
Yeah, maybe I'd slightly disagree with that. I think obviously the knowledge did grow, but there was also, even contemporaneously with that, there was people using the same data set arriving at
I would challenge you
answers.
to point that out. I don't think that's true when you dig into it. Same catalog, but not all of the different characteristics of the survey.
Yeah, so maybe I think that's a fair point. They're using different analysis tools.
No, not just the tools. I'm saying you need not only the homogeneous catalog, but you also need the star properties, and you also need completeness and reliability based on transit injection and recovery. And transit injection and recovery gives you the completeness, but then we also had several tests that we did in order to characterize and quantify reliability. Those pieces are all important. You have to include them all.
Yeah. I think they were included, but we could maybe talk about that afterwards a little bit more detail. But I think, I spent some time reading some of those papers quite carefully. It looks like completeness and reliability, I agree, are absolutely central aspects of this problem. And I think it is widely understood that those are important things that you have to deal with if you want to get an occurrence rate. I guess my kind of main point here is I have a little bit of discomfort still with the E-to-Earth estimates that we have, and it would be great if we could
rightly so.
Have a follow-up mission like Plato or the Chinese are planning something to maybe finish this off. And it kind of leaves us in a difficult timing situation, because of course we would really like to start thinking ahead for a direct imaging mission, and the size of that mission is going to be affected by if it's 1% or 100%. That would have a giant impact on how you would design that mission. So I guess my question is, how comfortable are you with the current E-to-Earth estimate? Do you think you're happy with that last Steve Bryson paper, or do you think there's more to do there?
Absolutely, I'm not happy. No, the state of our knowledge is imperfect because we had to extrapolate. I'm not going to believe anything that's based off of extrapolation. Mm-hmm. I want a measurement. But also, we know it's not zero, right? I suppose there could be some like weird discontinuity where all of a sudden nature just stops making planets. But we already know that that's not true because Earth exists. So I think that would be a highly unusual and very, not acceptable outcome. So I'm not willing to believe that. But we know that planets in general are common. So I'm comfortable enough with what we've done to justify doing a future direct imaging mission. I'll go on the record as saying that I think it's significantly underscoped. I think we need a bigger collecting area. I don't think that we're going to be able to find evidence of life without a statistical sample. Every single mission I've ever studied has not, I won't say overstated their case, but it's been very, has played this game of just having enough science to justify the mission, but not too much to call into question the expenditures, right? So it's always a cost-benefit game.
Yeah, which was true of Kepler, right?
Which was true of Kepler, and our budget was cut, as we talked about before, so we had to make adjustments and reduce the scope even further, which impacted the detectability. So, and nature gives you surprises. Like the stars ended up to be more variable than we thought, and so that was an issue. Had the rolling band artifacts, those things you can't predict. So what surprises are we going to have in the future? But more importantly than that, I just don't think that the state of our knowledge is such that we can say that is a biosignature, detect oxygen and say that's a biosignature. It has to be put into the broader context. Because there are abiotic sources of oxygen in an atmosphere, and we don't understand all the forms that life could take or what all the different possible biosignatures are, and nature is too surprising. So what I would like, if I could choose, would be to say that you're going to observe, a large many dozens of atmospheres of terrestrial-like planets in the habitable zone, and then look statistically at their characteristics, you know.
So you, yeah, I guess I would agree that it'd be better to over-engineer it rather than engineer it just
I think
the minimum
well,
necessary to complete the goal.
it's a combination thing. I mean, I would love to say that's true, but yet the realities are that we can't spend money unnecessarily or haphazardly. So we have to use taxpayer money wisely. But in this case, because we don't yet know, to understand life, what life is, you have to understand what life is not. And what I mean by that is when we look at atmospheres and all of the chemical constituents in that atmosphere, you're making a huge leap to say that one of those chemicals is from a metabolic byproduct of some life that you don't even understand. All you know is what life looks like on Earth and what those metabolic byproducts are on Earth, okay? So, and there's all kinds of geological processes and chemical processes that we're just now learning about that contribute to the diversity of exoplanets. So because there are so many unknowns, what I would like to do for this first step is have a statistical sample of these kinds of planets, look at their chemistry, look at their chemical constituents, and maybe life will stick out like a sore thumb. Maybe a living world just really looks different than a non-living world. I think that that's our best hope of finishing that mission and being able to say that life exists beyond Earth.
Yeah, obviously, it's an incredibly exciting goal to try and detect life, and we're not quite there yet with our current instrumentation, but one very exciting additional program, leaving the world of Kepler and going forward, is of course JWST. And you're one of the leaders of one of the largest early release science programs, the ERS programs for exoplanets that was happened, I guess, what 3 years ago now, that program?
It was selected, I think, in 2017, but of course it took a while.
Because it was the delays.
It was delayed. Yeah, it was the largest early release science program of all the disciplines.
Wow. So yeah, I want to ask you, how did that program come to be, and what do you think are the lessons for us from that program?
So there's a long history to that. At some point, I was involved with the NASA's Nexus for Exoplanet System Science, which was an attempt to kind of coordinate all of the various NASA-funded exoplanet programs that had that were thinking about the future of this life detection, right? This long-term goal, and we would get together every once in a while and think strategically. You know, how can the community help to mobilize progress in our field? What can we do to communicate science to our stakeholders, to not lobby, but advocate for our science out on Capitol Hill, and to organize our community so that we all have a common goal in terms of how to find life, because we don't want that to be contentious, or we need to have our ducks in a row when the opportunity arises. So we thought a lot about those kinds of questions, and we'd had these kinds of meetings. And one of the questions that emerged was, well, how are we going to decide as a community what JWST should first look at to best position us to use that instrument? Because JWST is an infrared instrument, so it has a finite lifetime. The baseline lifetime was like 5 years, very short. This is very different than Hubble, which is serviceable, right? So we wanted our community to hit the ground running and like immediately learn how to use the data, analyze it, understand its limitations, to be able to put forward the best possible proposals. And so with that in mind, kind of concurrently, there was Kevin Stevenson, who was working with some of the Atmospheres community to think about this question. And we joined forces, and we just put out an open call through the Exoplanet Program Office for people to come and think about it. And that's what gave rise to this working group. And the working group, when it started, I mean, instantly we had like 100 people that were weighing in, and we would have weekly meetings, and this went on for like a year. And very methodically, very carefully, thoughtfully, with a lot of different expertise and perspectives, we kind of came to the conclusion of what we wanted to do, what we thought was the best thing to do for our community. And that turned into this early release science proposal.
Great. Yeah. And what were there was 3 planets, was it observed? And
Yeah.
these are all hot Jupiters, I think.
They're all hot
Trying
Jupiters.
to hit all the different instruments.
Yeah, we didn't want to push the envelope. We just wanted like something we knew that was well studied from the ground, very strong signal. But we wanted to test all instrument modes. We wanted to test all transiting phenomena, both primary transit, secondary transit, and phase curve. Let's see, it seems like there was another axis. Those are the primary ones. So we set out to do that by observing 3 hot Jupiters, one in transmission in all the instrument modes, one as a phase curves observation with actually another instrument mode at the longest wavelengths, that's MIRI, and then one in secondary eclipse.
Yeah, it was a great because that kind of gave us all, we were all desperate to see how good the data was. That was our first
This
look.
last target, WASP 18b, so the first one was WASP 39b, WASP 43b is the one that has the phase curve, and then WASP 18b was the one that we observed in secondary eclipse. And that star is extremely bright. So we thought that would push the limits on the bright end to see what was possible and see if that affected the noise floor at all.
Because if you go too bright, you kind of saturate the detector essentially.
Yeah, you can potentially get into nonlinear regimes where things with the instrument go wonky. Of course, you can saturate or it affects pointing. There's a slew of things that can happen. There might be some hysteresis in your detectors that can be infected when you're swarming it with so many photons. So, we wanted to take a look at all those things. And also, hopefully, come out and say, Webb is capable of, getting down to 10 ppm or whatever it is. So that was the goal.
And, this program has obviously led on to so many, we heard about it yesterday. You gave a lecture here that was wonderful, talking about all the science coming out of JWST on exoplanets. And it was startling that you mentioned how in the 20 years of Hubble observations, there was something like a couple of dozen exoplanets that had been observed spectroscopically. Mm-hmm. And already in 3 years, JWST has totally eclipse that. It looked like a factor of 2 or 3 more planets. At
least. I think in cycle 1, there were something like 70 planets that were observed. Yeah. So if we can do that for 10 years, that's 700 planets, or maybe half that if you take multiple observations of planets. So that's a potential to have a really incredible legacy.
Right. A massive goldmine of data. And what do you think the primary scientific questions are that you are most interested in to pull out of that treasure trove of spectra?
There's so much work to be done. And I have my favorite science question, which I think you already know the answer to, but I will tell you it anyway. But maybe I almost wonder if we as a community were maybe too naive in the beginning. There's just so much work that needs to be done in terms of understanding the data, but also finessing the models of how to create a planetary spectrum, but also how to interpret the planetary spectrum, how to take care of disequilibrium, chemistry or photochemistry. There's all kinds of physics that goes into the models that is really getting spun up. But I think that there are 2 really important questions that are related to habitability in the future. One of those questions is, do rocky planets orbiting M dwarfs, are they capable of retaining an atmosphere? And the reason that's not obvious is because these M star hosts, when they're very young, they're extremely luminous. And so what you observe as an exoplanet in the habitable zone today had a very different history. It was basically bombarded by irradiation from its parent star, not just normal, radiation luminosity as we think of, but also high energy radiation, because when these stars are young, they're very magnetically active. So that was a pretty hostile environment to grow up in. So it could be that in those early phases, any kind of atmosphere of volatiles could have been stripped away.
So it's like the TRAPPIST-1 type programs that would maybe address this. Yeah.
Yes. TRAPPIST-1, but there are others. We are beginning to identify other what I'd call temperate planets orbiting M stars, relatively cool today, where we can test this. So we'd like to be able to see that these planets are capable of retaining an atmosphere, because 70% of the stars in the galaxy are M dwarfs.
It's a big hit if they're out.
It's a huge hit to the propensity or the possibility for life.
Yeah.
So that's one question. The second question has to do with the planets that right now are the most populous in our discovery catalogs. These are planets that are intermediate in size between the terrestrials in our solar system and the gas and ice giants in our solar system. And, so we've got the tiny things that orbit close to the sun, we've got the big things that orbit far away, and we've got nothing in between. And yet that is the most populous type of planet in the discovery catalogs, but it also turns out in the galaxy, if you're considering planets orbiting interior to one astronomical unit and larger than Earth. So that's remarkable.
Yeah.
What are they? We don't know. They seem to be, some people call them kind of scaled down Neptunes, warmer scaled down mini Neptunes. Some people call them super Earths. Those words invoke very different images. But the bottom line is, even if they are scaled down mini Neptunes, there are scenarios where such a planet could be amenable to life, right? There could be a scenario where you'd have liquid water in contact with rock at a pressure where complex molecules do not denature. So we need to understand that, because that could be an entirely new, frontier for finding evidence of life. So that's really exciting to me, where you go out and you look at something, you kind of lift the veil to things that you couldn't see before, and all of a sudden you have this big surprise. So I think JWST could really make headway on understanding the diversity of that population, their chemistry, maybe even their interior structure and composition.
Yeah, and maybe to finish this off, because I want to be cognizant of your precious time today. It's often, I think when you look back at Kepler, and even to some degree the ERS program, the early JWST work, it's easy to think that there was a kind of a golden period of exoplanets, of any field. There's an episode where it seemed like, oh man, I wish I was around then, because it seemed like there was so much activity happening. What is your projections for the future, and what would be your advice to maybe a young person who is interested in astronomy and are thinking, is exoplanets the right thing for me, or is this a field which is winding down, or a field which is exploding? I think I know what you're going to say, but I just was curious how you'd answer that.
I was going to say the golden period is always in the future. Even on cosmic terms, I think the heyday of life could be in the future of our galaxy. Maybe we're not in the heyday of life for our own galaxy. I feel a little bit gloomy these days about our political situation, so there's that that pops into my head as I think that. But I started out as a stellar astrophysicist. Stellar astrophysics was not particularly well funded. The Hubble Deep Fields were, creating a lot of really high-profile science, and cosmology and extragalactic science were like where the money was at during those days. I never really thought too much about that. I always just kept doing what excited me, what interesting questions there were, and how I could best contribute to them given the circumstances, right? We have all these life experiences, and we learn certain things, and questions pop into our brain, and we know that we can answer them. And so you set out to do that, and that's exciting. And I would say to young people that they should do that, do what excites them. Of course, the practicality is that the jobs are dictated by where the money is at. And so we have to also be flexible. And the reality is that we're all interested in everything. That's the secret, right? We're scientists because we're curious, and everything in astrophysics interests us. So when I saw that report on Gabor Basri's desk about FreeSip, it did spark curiosity. And it was against the backdrop of the first discovery of the exoplanets, and I saw how my field could contribute to that, how my expertise, I have the skills to do that. I know how to answer that question, right? And when you feel that, you do it. You just do it. And so, I don't know. We have to be flexible in science. We have to be adaptable. We have to be willing to learn new things and not be afraid of new challenges, and leverage our strengths, which is to lean into the curiosity and the passion that drives us.
Yeah, I love that answer. Well, thank you so much for your time, Natalie.
You're very welcome.
Appreciate you
David.
have to run now, so thank you for finding time to sit down with me today.
My pleasure. Thank you
Yeah.
for bringing me to New York, despite the cold.
Yeah.
It was really wonderful to be here and to spend time with you.
So that was my conversation with Natalie Batalha, and I'm very grateful for Natalie for making the time to join us on the podcast, and hopefully you learned a lot from that conversation. You know, talking about Kepler, it really is like a walk down memory lane for me. I mean, as I said, during that conversation, for myself, but for dozens, I think hundreds of young astronomers at the time, and some older astronomers as well, it really was a transformative, career-changing experience. Even though I wasn't involved in the team, you know, I was always off to the side as kind of a strange outlier who wasn't part of the Kepler team, but was using a lot of the Kepler data. But there were many people, both inside the team and outside the team, who were trained, who learned how to do the cutting edge data science analysis of these time series photometric data using Kepler. That's how we learned to discover transiting planets. That's how we learned to look for exomoons in my team. That's how we learned to measure transit timing variations, to look for orbital decay, to look at phase curves, secondary eclipses. There's so much science that just poured out of this mission. That's just the planet stuff. On top of that, there's all the star people doing astroseismology and variability studies, rotational studies, gyrochronology. So the gift just kept coming. And I remember at the time, it was kind of like drinking from the fire hose. People would say that phrase. The amount of information and data we were getting about planetary systems was just so unprecedented. It was more than we could dream of. And yet it delivered, and it just kept coming. So it was a very exciting time to be a scientist. And there are ebbs and flows in this story of discovery. And I think that was definitely one of the real flows when we were just getting lots and lots of data. And when Kepler ended, TESS took over, and TESS has continued to discover many thousands of planets itself at this point. But kind of the sheer exponential rise that we had during Kepler, I think, is very difficult to keep up with. But the way we are learning about exoplanets is changing. I think we're going beyond the sheer counting. You know, that was the obsession early on in the years of exoplanets. Let's just try and find hundreds, even thousands of planets and look at their properties, their demographics, and learn about them. But as time is evolving, I think we want more detailed information. We don't just want to know their orbital period and their size. We want to know about their atmospheres. We want to know about their environment. Do they have moons? Do they have rings? Are they ablate? We want to know all these other properties about them. And so I think that's kind of the transformation that's happening now. That's the flow that exoplanets is going through. We are maturing as a field. I think pure counting, as important as it was in that time, just to sort of figure out what the landscape was, we are now trying to go to this phase of detailed characterization. So that's just to say, you know, I think it's easy to listen to the early days of exoplanet discovery as a young person and think, man, I wish I was around then. Because, you know, it's like you always wish, I wish I was a scientist a few hundred years ago where you could just drop wood into, you know, a river and say, look, it floats, give me a Nobel Prize. And science in some ways seemed like it was easier back then, but it was also incredibly difficult to actually figure out the way the world worked for the first time when you had no context. And the same way, it was both difficult and rewarding work to discover those first hundreds, thousands of exoplanets. But as a young person, as someone getting interested in the field right now, I would just say like the future is extremely bright because we are moving into a new phase thanks to James Webb, thanks to upcoming missions. Beyond that, like the Ariel mission in Europe, for instance, that are going to characterize more atmospheres. So I think there is a very bright future ahead of us to transform our understanding beyond just points. And obviously Natalie's career really spans that. You really go from Kepler to James Webb and even now the early planning stages for this, hopefully, next generation habitable worlds observatory. Maybe in the 2030s, if we're lucky, we might see something like that. So the future is bright, and it doesn't always feel like it, that the future is bright. But there are storms and there are ebbs and flows to everything. And I think in the long run, I would still say this is an amazing time to be a scientist, and there's a huge amount left to discover. So I want to leave you with that final note. As always, I want to say a huge thank you both for watching or listening to this episode, however you're ingesting the Cool Worlds podcast. And if you want to support what we're doing, the best way to do it is to head to coolworldslab.com/support. That is coolworldslab.com/support. And then you can donate to my research team. And by donating to my research team, not only does your money go directly to research, which I think is kind of cool, but also it kind of frees me up from writing grants. And I can spend more time making these podcast episodes and the main channel episodes as well. So that's the best way to support us, and very grateful to you. If you think we deserve to have funding that way, please do consider clicking the link which I'll put down below in the description and in the show notes. So thank you, and I'll see you all in the next episode.